Hi guys, welcome to our 7th lecture on our course on photonic devices. On today's lecture, we'll keep talking about the density of states, and we are going to extend the concept to define a density of states as a function of energy E. On our last lecture, we talked about the density of states as a function of wave vector k. And on today's lecture, we'll extend this concept as well as do one exercise. So just as a reminder, at the end of our last lecture, we found the expression for the density of states as a function of k, which was just this, k squared over pi squared. And we found this by considering the k-space, and in the k-space in particular, the two spheres, the surface of the sphere with radius k and the surface of a sphere with radius k plus dk, and we basically counted the number of points, discrete points, since the points in k-space are discrete, as we've discussed. So we merely accounted for all of the points, all of the states between the surface of the sphere with radius k and the surface of the sphere with radius k plus dk. So that's how we found, by using some geometric considerations, we found this expression right here. So we'll start from this and calculate rho as a function of E from this expression. But we'll also use this expression right here, which we've also seen, and this expression comes about from the fact that rho of E, dE, is the number of states with energies between E and E plus dE. So if we draw the band structure and we consider, for example, the conduction band, right? Just the values close to the band edge. So you have E as a function of K, and you have the edge of the conduction band here. And we saw that the points, the states, or the EK pairs in the band corresponding to the allowed states are discrete, right? So if we draw these points, they would look something like this. And for each point that you have on this side, you have points on the other side as well. And the points become denser as you go deeper into the band. So you have more points per energy. But the point is that these points are discrete. And if you account for the points with energies between E, let's say this is energy E corresponding to this point right here with a K value K, and you consider a differential E, so that this right here is E plus dE, right? You have the corresponding K value right here, K plus dK. If you calculate the number of states by this way, which is taking into account all of the states between this energy and this energy, or in this way, which is taking into account all of the states with K's between this and this, you get the same number, basically because the number of points between here and here is fixed. So you have the same number of points within this interval. So this is what this expression means, basically. So the term on the left corresponds to the number of carriers or electrons, or more accurately, the number of states, right? Because these states need not be occupied with energies between E and E plus dE per unit volume. And also, the term on the right here corresponds to the number of states between K and K plus dK. And, well, as we saw, these two things give us the same number of states. Now, if this is valid, you can verify that this is also valid. So rho of K has to be equal to rho of E times the derivative of E with respect to K. And by isolating rho of E here, we can calculate it. So therefore, rho of E is equal to rho of K divided by the derivative of E with respect to K. Okay. Now we have this. This is K squared over pi squared, right? We just found this out. So this guy right here we have. We just have to get this part right here, and we find rho of E. Well, we don't have an analytical expression for E as a function of K for the whole band for any semiconductor, but using the parabolic approximation, we saw that close to the band edge, what we had was this, right? The band structure could even have, or usually has, a complex structure like this. It could be something complex, but close to the band edge, EC for the conduction band, this could be approximated by a parabola, right? And for this, we do have an analytical expression for this parabola, which we can differentiate with respect to K, because it's a function of K. So we get, at least for this region, an expression which is valid and can be used to find rho of E. Okay, at least for the region close to the band edge here. So if we have the derivative of E with respect to K, dE dk, we can find rho of E. Okay, why do we want to do this? Why do we want rho of E instead of rho of K? Well, it's more useful because we usually describe the phenomena in the bands in terms of energy rather than wave vector K. Okay, so that's why this is a much more useful quantity. Rho of K was just a means to get to this. So we'll use the parabolic approximation as we've discussed. So this approximation gave us E as a function of K, at least goes close to the band edge. So as we said, you have E as a function of K, and this gives us an expression for a parabola close to the band edge EC, which is this, right? So note that this is a function of wave vector K. When K is 0, you're right at this point here, and as you get away from this point, you have the parabola. So K squared term here describes a parabola multiplied by a constant. So nothing new here, and this is only valid for E larger than EC. If we differentiate this with respect to K, what do we get? Well, EC is just a fixed band edge energy here. The derivative of it will give us 0. Okay, so this will go away. And, you know, since we're differentiating with respect to K, you get this 2 here drops, and you get 2 times h bar squared over 2 m star times K. So this is what you get, right? EC goes away, and the 2 in that drops from the derivative cancels out with the 2 in the denominator, and you get h bar squared times K divided by the effective mass of the electron. So this is what we wanted. Now we have all the means to get rho of E, right? Since, as we said, rho of K, we found out from before that it was K squared over pi squared. We can substitute it right here, and this term right here is what we just found to be h bar squared times K divided by the effective mass. So if we divide this by this, what do we get, right? So pi squared does not cancel out, so it stays right here. Neither does K squared, so K squared over pi squared just remains in the resulting expression, and you flip this upside down, right? So M effective over h bar squared times K. Now the K squared cancel the squared, and the K squared cancel with the K, and this is what you get. So M effective divided by h bar squared times pi squared, and this whole term is multiplied by K in the numerator. And this is the resulting expression for rho of E, but it still gives us a result that is a function of K, right? How can we replace this? Well, we can use the parabolic approximation itself to get an expression for k as a function of E. So we can replace k in this last expression by isolating k in the parabolic approximation. Now, originally, the parabolic approximation gave us E equal to EC plus k squared multiplied by h bar squared over 2me star. So if we isolate this, right, we get this expression right here. So if we isolate k on this expression, we get this right here, which we can then replace right here in place of the k. Okay. Now this is the resulting expression, right? And this is the term that we replaced by k from the parabolic approximation. Okay, this term right here was replaced here, so you get this constant here, m star over h bar squared times pi squared, appearing here, and then this is the k term. So rearranging, we have the density of states as a function of E. So notice that you have m star here and the square root of m star right here. So this corresponds to m star to the power of 3 halves. The same thing happens with, and you also have h bar squared here, and the square root of h bar squared, which is h bar to the power of 3, so it has to appear here squared inside the power of 3 halves. But this is basically the same expression with a few, with a little manipulation, okay? This is more often used in this form right here, but it's the same thing. And by doing an identical procedure, you know, and using the parabolic approximation for the valence band, you get this expression, which is a very similar expression, except that note that you have mh star, which is the effective mass of holes here, because we're talking about the valence band, and the E term and the band edge term here are flipped. So instead of E minus EC, you have EV minus E, but very similar expression for the density of states in the valence band. Okay, so this is in the conduction band, this is in the valence band. Therefore, the range of energies here are going to be higher than EC, and this you have energies lower than the band edge for the valence band. But these two expressions are the density of states as a function of energy in both bands. These are the density of states in the conduction and valence band. In the valence and conduction bands, rho of E grows from the border, from the band edge towards the center of the band, as we've discussed. If you look back in the expression, right, as you go towards energies that are larger and larger with respect to EC, so as E gets larger than EC, this term right here grows, and the density of states grows. Granted, it grows with the square root of E. If you recall the expression for rho of K, it grew with the square of K, right? With respect to E, rho of E grows with the square root of E, so it does not grow as fast, but it still, as you get E larger than EC, rho of E tends to grow. And the same thing will happen here, except that as E gets smaller than EV, this term will be positive, and will get larger and larger as the energy gets lower than EV. So away from the band edge EV, you have a larger term which will correspond to larger density of states. So as you move towards the center of the bands, away from the band edge, there are more states available. This is illustrated right here. You have the band structure for the conduction band and the valence band. And in this case, the states are represented by lines, but you know, these lines are giving us these points right here. And you get a larger density of states as you get away from the band edge EC. The same thing would happen here. As you get energies lower than EV, the states will be bunched up and be closer together. And as you move in towards the center of the band, you have more and more states. Okay, so as we said, if you look at the expression, you should see that the density of states is not a constant as a function of energy. It grows with the square root of the energy. So therefore, this gives us the distribution of the states. They're not uniformly distributed. They grow with the square root of E away from the band edge in the conduction band and the valence band as well.